Good evening, everyone who have joined us today live for the session of NCRT Class 12 Physics Solutions. Today we are taking up the chapter Alternating Current, chapter number 7. As you guys know, that NCRT forms the basis for your CBSE Class 12 board examinations as well as for your NEET UG preparation. And this chapter is also important for the JEE mains and advanced preparation. So here today we will be taking up 8 questions which are given in the NCRT exercises, and we'll understand the formula, the application of the concepts related to each question, and that should put you in a good place to begin your preparation for your 12 course as well as NEET and JEE. So a brief introduction about myself. I am Sashwat Mishra, and I'm currently a third year MBBS student at AIMS Raipur. Previously, I was at IIT where I was in engineering physics branch, and I scored 9.8 CGPA before dropping out to pursue MBBS from AIMS Raipur. So that's all about me. Before beginning with the session, I would like to inform you that these series of videos are available free on the YouTube channel. So if any of you guys are interested or inspired by these videos to learn from us on direct batches, one-to-one guidance, and proper timely evaluation test series, you can approach us by the contact number which is given below in the description of this video. And one more thing, that if anyone has any doubts while solving the question, you can type it live in the YouTube comment section. After finishing with all the questions, I'll take a look, and if anyone has any doubt, then we'll try to clarify it here. Then we will end the session. So that being said, without much further ado, let's begin with today's NCRT Class 12 Solutions series of physics. Today we are taking up alternating current. Okay, so here's the first question right in front of us. Let's go through the question. A 100 ohm resistor is connected to a 220 volt 50 Hz AC supply. What is the RMS or the root mean square value of current in the circuit? And what is the net power consumed over a full cycle? So we have been given that the resistance of the circuit is 100 ohms. Okay. The source voltage is 220 volts and the source frequency is 50 hertz. So this information we have been given, and to determine the RMS value of the current, we can directly use the Ohm's law, which is I equals V upon R. Okay. For determining the RMS current, we can directly use the Ohm's law. In this case, it will be 220 over 100, which is just 2.2 amperes. So the RMS current which has been asked is 2.2 amperes, and this is the answer. Now for the second bit, what is the net power consumed, the total power consumed over one cycle? That also we can calculate by the conventional formula for power in current electricity, which is P into I. Your voltage is 220 volts and your current is 2.2 amperes. So this is just 22 squared, which is 484 watt. So net power, the net power in one cycle consumed is 484 watts. That is the answer to this question. Okay, so nothing difficult here. Let's move on to the next question. Here's the second question in front of us, and it says the peak voltage of an AC supply is 300 volts. What is the RMS voltage? So let's first solve the first question. We have been given the peak voltage, that is V naught, or the amplitude of the voltage is 300 volts. All right. And we know this formula that the RMS value of the voltage is V naught upon root 2, right? The RMS voltage is related to the peak voltage by this relation, which is V naught upon root 2. All right, I guess everyone is clear up to this. So substituting the value, we have 300 upon root 2, which is 150 root 2 volts, which is 212.2 volts. Hence the RMS voltage in the question is 212.2 volts. This is the answer. Let's move on to the second bit, which says the RMS value of current in an AC circuit is 10 amperes. What is the peak current? We have been given the RMS current, or the root mean square current, is 10 amperes, right? Now, similarly, for the current, the relation for the peak current with the RMS current is peak current equals root 2 times the RMS current. Okay, so you need to remember two formulas here. That is, RMS voltage is peak voltage upon root 2. Okay, and RMS current is peak current is RMS current times root 2. Or you can also remember it as the RMS current is peak current upon root 2, just like the voltage relation, right? Okay, so here we are asked the peak current, so the I naught will be root 2 times 10 amperes, which should be your 14.14 amperes. So the peak current has to be 14.14 amperes. This is the answer to this question. Okay, I guess these two formulas you will remember. Okay, all right. So let's move on to the next question. A 44 milliamp inductor is connected to a 220 volt battery a 50 hertz AC supply, not battery, AC supply. Determine the RMS value of the current in the circuit or through the inductor. Okay. So the inductance which is given to us, the inductance L is 44 mH, which is equals to 44 into 10 raised power minus 3 H in SI units, right? And the source voltage is 220 volts. If nothing is said, then this is actually the RMS voltage, okay? And the frequency of the source is 50 hertz, okay? Now, the omega of the source, angular frequency of this source will be 2 pi f, right? Which is 2 pi into 50, which is 100 pi. Okay. Now, the inductive reactance, the inductive reactance of the circuit, that is chi L, can be calculated as that is omega times the L, right? Which is 100 pi times 44 into 10 raised power minus 3, which is again 4.4 pi, right? This much ohms. Now, to find the RMS current, okay, the RMS current in the circuit, we have the RMS voltage is given in the question upon the reactance of the inductive reactance in this case of the circuit, which is 220 upon 44 pi. Here will be a 10, right? So if you cancel this is 10 to 50 over pi, which is 15.92 amperes. So this is the IRMS, or the RMS current, which is asked in the question is 15.92 amperes. This is the answer to the question. So you need to remember this formula here, that is IRMS is Vrms upon the inductive reactance, or that can also be written as the peak current equals the peak voltage upon the inductive reactance, okay? Because IRMS is I naught upon root 2, Vrms is V naught upon root 2. So root 2 will be cancelled from both sides. So you can get the same relation with the peak current as well as the RMS current, right? Okay. So I guess this question is clear to everyone. So let's move on with the next question, which is a 60 microfarad capacitor is connected to a 110 volt 60 hertz AC supply. Determine the RMS value of the current. The previous case was an inductor, and this case we have a capacitor. Okay. So let's see what have been given to us. The capacitance the capacitance C has been given to us as 60 microfarads. Okay. So if we convert it to SI units, it will be 60 into 10 raised to minus 6 farads, right? The source voltage also, if nothing is mentioned, it refers to the RMS voltage, which is 110 volts. And the source frequency, which is given as 60 Hertz. Now the angular frequency approach is similar to the previous question, right? The angular frequency omega would be 2 pi f, okay, which is 120 pi, okay, because f was 60 hertz, right? Now, in the previous case, we had to calculate the inductive reactance. In this case, we'll calculate the capacitive reactance, chi c, right? Chi c is 1 over omega c. Inductive reactance is omega times L, okay? So this also you need to remember in the previous question, okay? Inductive reactance is omega times L and capacitive reactance is 1 upon omega c, okay? Which is 1 upon 120 pi. Here will be 10 raised plus 6. Here will be 60. This 10 raised per 4 upon 6 into 12 pi ohms. This is the capacitive reactance, okay? Now, the RMS current, as usual, is asked. RMS current, okay? That will be the RMS voltage upon the capacitive reactance, right? So it will be 110 volts upon 6 into, sorry, the capacitive reactance is 10 raised power 4 into 6 into 12 pi amperes. So IRMS would be, if you solve it, it is 2.49 amperes, which is the answer to this question, okay? So once I'll just summarize the formula that the reactance for a resistor, okay, is just the resistance itself, okay? The reactance for an inductor is omega times L or 2 pi f times L, and the reactance of a capacitor is 1 upon omega c, which is 1 upon 2 pi f into c. Okay. So this is a list of formula you need to know. Okay. And another listing, the IRMS is VRMS upon the total reactance, and the I naught or the peak current is V naught upon the total reactance. Okay. So these two things you need to keep in mind. Okay. So let's move on to the next question. Okay, which is question number 5. So let's read out the question first. In the previous exercises, that is 7.3 and 7.4, what is the net power absorbed by each circuit over a complete cycle? And explain your answer. Okay, so let's first consider exercise 7.3. Okay, where we had this inductor. Okay, and we got the RMS current this much. We had the RMS voltage this much. Okay, so let's just write those facts here. The RMS current was 15.92 amperes. The RMS voltage was 220 volts, and the power, the net power consumed is VI cos phi, right? Everyone knows that this phi is the phase difference. This I is the phase difference between V and I, right? So here another formula you need to know. P equals VI cos phi, right? Okay. Now, the 7.3 example was a purely inductive circuit, right? It was a purely inductive circuit. Okay. And for a purely inductive circuit, the difference in the phase or the phase difference between the potential, that is V, and I is 90 degrees, right? That means what is the meaning of the phase difference between V and I? That means whenever the potential is at the highest, that is whenever potential is at V naught, the I will be at the minimum value, and the potential is at the minimum value, I will be at maximum value, right? So that is the meaning of the potential difference being 90 degrees. Okay. So here I'm writing it for you. Okay. So we'll plug in this value of I equals 90 degree, V and I, we got everything. Okay. But as you know, your cos phi happens to be 0, right? Cos 90 happens to be 0. So the net power consumed in the total cycle is again 0, right? So this is the answer to the first part. Now in exercise 7.4, we had the RMS current, which is 2.49 amperes. Okay. The RMS voltage was given to be 110 volts. Be careful about the units. Okay. So volts, and again the net power will be VI cos phi, and 7.4 was a purely capacitive circuit. It was a purely capacitive circuit, and in this case the phase difference between the potential and the current is again 90 degrees. Okay, so cos phi is now 0, and hence the net power consumed will again be 0. That's the answer. Now here I will again write out the five values. Okay, five values for a purely resistive circuit would be 0 degree. For a purely capacitive circuit would be 90 degree. And for a purely inductive circuit is again 90 degrees. Okay, so here you need to remember this and this relations. Okay, so it follows from this part that for a purely capacitive and purely inductive circuit, the net power consumed over the entire cycle will be 0. I'm not saying the power consumed will be 0 for the entire cycle. The net power for the entire cycle or one cycle will be 0. But again, in between, it will consume power, of course. Okay. So I guess this question is clear to everyone. Yeah. So if this is clear, we shall move over to the next question, right? Okay. So here is the next question in front of us. Yeah. So a charged 30 microfarad capacitor, a charged 30 microfarad capacitor is connected to a 27 mAh inductor. What is the angular frequency of oscillation of the circuit? We are being said that we have a charged capacitor. Okay, we have a charged capacitor of 30 microfarads. Okay, and this is connected to an inductor. Okay, this is connected to an inductor of inductance 27 mAh. Okay, so this is the case of a LC circuit, right? This is a case of LC circuit. So in this case, we have been asked to find out what is the angular frequency of free oscillation of the circuit. Now, what do you mean by the oscillation? As this is charged, the capacitor is charged. So charge will first flow from here to the inductor and back into the capacitor, right? The capacitor will get charged and discharged multiple times. That is known as the oscillation, okay? Not in a mechanical sense, okay? So what is the angular frequency of those free oscillations? So we have the formula, that is the angular frequency of the free oscillations are in a LC circuit 1 over square root of L times C, right? So we'll just plug in the values. So you have to remember this formula first of all. Okay. So you remember this formula and it would be 1 upon square root of L, which is 27 mAh times 30 microfarads, right? So this one will have 1 over square root of this will be 3 to the power of 4 into 10 raised power minus 8, right? So it will be 1 over 9 into 10 raised power is 4. So the angular frequency would be 10,000 over 9. Okay. So this is 1.1 into 10 raised power 3. The unit of angular frequency is radians per second, right? And this will be the answer to this question. Okay. So here you need to know the formula for find the angular frequency of oscillation on an LC circuit is 1 upon root L times C. Okay. So I guess this is pretty clear to everyone. So shall we move on to the next question? All right. So here is the next question. So let's read out the question first. We have a series LCR circuit. Okay. So let's first draw. We have a series LCR circuit. That means we have all the three components. We have a resistor, we have a capacitor, and we also have an inductor. This is the series LCR circuit, which is connected to a variable frequency, 220 volt, 220 volt AC supply. Okay. So here is the circuit diagram. Okay. So this is 200 volts, sorry. It's a 200 volt AC supply. Now AC supply, we can denote it like this also. Okay. So a 200 volt AC supply, and we have the resistor as 20 ohms, the capacitance as 35 microfarads, the inductance as 1.5 H. It's not milli H, it is H. Okay. So we have the values over here. Okay. And when the frequency of the supply equals the natural frequency of the circuit, that is when they are in resonance, what is the average power transferred to the circuit in one complete cycle? Okay. So we have been given all the values, and first we need to find the impedance of the circuit, right? Impedance C, which can be given as the square root of R square plus the reactive inductance minus the reactive capacitance whole square. Okay. But at resonance, we have been given the condition that they are in resonance. So at resonance, we should remember that these chi L and chi C are equal. Okay. So this is a concept you should remember. So what will happen? This term will tend up to be 0. So you'll have the impedance as this R, right? Which is 20 ohms. Okay. Now we are being asked what is the average power. Okay. So first let's then find the current, the RMS current, which is the RMS voltage. This is RMS. Nothing is said means it's RMS, okay? Upon the Z rate, which is 200 upon 20, which is 10 amperes. So the average power consumed would be this RMS current times the RMS voltage, okay? Average power over one complete cycle, that is the net power only, okay? Which is uh, 10 amperes times 200 volts, which is 2000 watt or 2 kilowatts, okay? So 2 kilowatts of power will be consumed by this LCR circuit, right? This is a LCR circuit. 2 kilowatt of power will be consumed in one cycle, okay? So here you need to know this formula for the impedance, and at resonance you need to remember the reactive inductance and reactive capacitance equal each other, okay? So I guess we are done with this question. So I hope it's time to move on to the next question. Okay. So here comes the next question, and this is the last question. Okay. So we have this source and LCR circuit. Okay. We have L, C, and R connected to a variable frequency of 230 volts. Situation is just like the previous case where this is uh, this is 230 volts. Your inductance is 5H. Your resistance is 40 ohms. And your capacitance is 80 microfarads or 80 into 10 raised power minus 6 farads in SI units. Okay. So this much information has been given to us. Now, in the first bit, we are asked determine the source frequency which drives the circuit in resonance. Okay. So let's approach the first bit. So at resonance, at your resonance point, you know that chi L will be equal to chi C. Okay. So from this relation, what is chi L? It is 2 pi F, that is omega times L is 1 upon omega C. So it is 2 pi F times C. So that implies 2 pi F squared is 1 upon LC. So that implies the frequency would be 1 upon 2 pi square root of 1 upon LC, right? So now we just plug in the values. L was 5, C was 80 into 10 raised by minus 6. Okay. So this will be 1 over 2 pi into 10 raised power 3. And this will be 400 below. So it will be 20, right? So 20, we can cut it 100, so 50. Okay. So the frequency would be 25 over pi. Okay. So if you calculate this using a calculator, you will have in terms of omega, it will be 50 rad per second, right? In terms of omega, it will be 50 rad per seconds. Okay. So this is the answer to the first question. Okay. And here you need to remember this formula directly. Okay. Yeah. So now let's move on to the second question. Obtain the impedance of the circuit and amplitude of current at the resonant frequency. Okay. Amplitude of the current means the maximum value of the current, that is I naught. Okay. Not IRMS. Okay. So move on. Let's move on. That we have to find the impedance and the I naught. Okay. So the second bit, we have found the omega as 50 radians per second. Okay. So the impedance would just be the square root of r square plus chi L minus chi C whole square, right? So R is 40 squared plus chi L is omega times L, right? Omega is 50 into 5 minus 1 upon 50 into 80 microfarads, right? 80 into 10 raised per 6 whole square. Okay. So this will be 50 into 5, 250. Okay. And this will be 2 zeros cancel and 8 5 are 40. So 3 zeros cancel. 3 zeros cancel from here. Okay. And here 4. Okay. So this is 1000 over 4. So it is 250 again, right? So this again turns out to be 0. Yeah, because initially also it didn't need to do this much also because at resonating frequency, we know that chi L equals chi C, right? So this term is 0. So this will just be the square root of 40 squared, which is 40 ohms. Okay. This is the inductance, impedance, the net impedance. And we have been given the RMS voltage as 230 volts. So we will find the RMS current first of all, which is VRMS upon the net impedance. Okay. So that implies the peak value of the current, that is I naught, should be equal to root 2 times the IRMS. Okay. So if you solve this, you will get the value as 8.13 amperes. So this is the answer to this question. Okay. So the third bit, okay, third bit, which says determine the RMS potential across the three elements of the circuit, that is through L, C, and R. Okay. Show that the potential drop across the LC combination is zero at resonating frequency. Potential drop at this combination is zero at the resonating frequency. We have to show that, okay? So now the RMS. So let's remove this question first. Okay. So yeah. So here across the inductor, the RMS voltage would be the RMS current times the IL, right? So which is equals to 23 over 4 times omega times L, right? So 50 into 5, which is 1437.5 volts. Okay. Now the potential drop RMS across the capacitance would be IRMS times chi C. It is IRMS, which is 23 upon 4 times 1 upon 50 into 80 into 10 raised plus 6 above. Okay. So if you solve this again, you get the same value. Okay. And the potential drop across the resistance is IRMS times R, right? So 23 upon 4 into 40, which is 230 volts. Now, the potential drop across the LC combination, which is asked in the question, would be IRMS times the LC combination. We always take chi L minus chi C, right? Which is 23 upon 4. And at resonance, we have been said that chi L equals chi C. So this turns 0. So this is 0. Okay. So also you can see that these values are equal. The magnitudes are equal, but the phase difference between them, the phase difference, okay, between them is actually 180 degrees. Okay. So if one is like this, the other would be like this. The waveform for both will be like this. So that's sort of a destructive interference, right? So it would be 0. So we have found out the individual potential drops across each component and also across the LC combination. We have shown that it is 0. So that is proof. So with this, we finish all the NCERT solutions to the alternating current chapter. Guess we discussed all the formulas also. I have marked here. So you need to keep in track with these formulae. Okay. So yeah. And one more thing before ending the session, I would again implore you guys that if you guys are interested and inspired by this series of videos, you guys can uh, choose to study from us with one-to-one sincere guidance, regular test series, and doubt clearance, and as a next level preparation for your NEET and JEE, as well as class 12 board examinations. So with this, again, we will meet after a few days with the next chapter solutions. Okay. So till then, good night and have a great life, everyone. All the best. Thank you.